Welcome to the Lewis structures lesson. Lewis structures help us visualize the different shapes and geometries that are in molecules. And so represents molecular structure through valence electrons. So the steps to start with for Lewis structures are first count the total amount of valence electrons and then two is to sort of see where are the imbalances. And so Lewis structures are sort of like a puzzle. And you have to sort of work around certain restrictions, whether that may be lone pairs. And so you're trying to get to 8 valence electrons on each of the atoms. They are trying to stabilize and get to 8. So 8 valence electrons is the goal. And so the goal is 8 valence electrons in which stability is reached. And so let's start by drawing the Lewis structure of water. And this will bring up a special case. So we have, let's just count the number of valence electrons first. So since hydrogen, oxygen, and then we have the total amount. So hydrogen is 1 valence electron, but since there's 2 of them, there would be 2. Oxygen has 6 valence electrons, so there's going to be 8 total. So we will draw it out. So usually the single element will be in the center, and then the element that has multiple will be on the ends. Doesn't matter where you put the bonds, it's still going to be correct. Now what's special about hydrogen is that if you were to say each atom needs to have 8 electrons or 8 valence, this would be incorrect. This is incorrect because hydrogen can only take up to 2. So what happens is oxygen needs to take in 4 or 2 lone pairs. So because of the fact that hydrogen can only take 2. So another example could be methane, CH4. Carbon would be in the middle. Hydrogen would be on each side. And in this Lewis structure, there are 4 bonds to carbon, so that's 2 electrons for carbon, so that gets you to 8. So that would be stability. And number 2, we have chlorate. So I see that chlorine has 7 valence electrons. Oxygen has 6. But since there's 3 oxygens, that's going to be 18. So the total would be 25. However, you have a minus, so that's going to be additional electrons. So that's 26 electrons. Chlorine goes in the middle, since there's only one of them. Oxygen, oxygen, oxygen. And so how I like to do this is based upon, and we also need the bracket. That looks kind of off. This looks like a better bracket. And we have a bracket signifying that we have added an electron. How I like to do it is each of the atoms needs to try to get to 8. So 6 times 3 is 18. And then my bonding pairs, 2 times 3 would be 6. So that's 24. So all I need is a lone pair on chlorine. So how I got 6 was there's going to be 6 more electrons on each of these oxygens. And so in theory, I would have 18 plus 6 would chart my bonding. And then I need to add on additional lone pair on chlorine to make sure chlorine has 8 valence. So in this case, I would have 6 on each oxygen and only single bonds, and a lone pair on chlorine. And make sure you have the dots next to each other. It's really important. So the next example that we have sulfate, and we have a -2. So let's just count how many valence electrons we have. So that's going to be 6. So oxygen again has 6 valence, times 4 is 24. And then the total would be 30, but in addition to 2, so that's 32 valence. So let's draw this out. Let's put sulfur in the middle. And let's just kind of do a square where we have 4 oxygens. So sulfur has a full set. So let's see. 6 times 4 would be 24. 2 times 4 would be 8. So that's like 32. So that's perfect. So that's saying all these, each oxygen has 6 on the oxygen itself. So then that's basically done. You don't need to have anything else, but you do need this bracket, or else it would be a different story. So let's just count again. 6, 12. So 6, 12, 18, 24, and then 26, 28, 30, 32. And you have 8 valence on the sulfur. You have 8 valences on each of the oxygens. So we have our next one, ammonium. And so again, this is sort of a process that is repetitive, and there's really nothing else. You just have to keep doing these steps. So nitrogen has 5 valence, and you can count the valences using the periodic table. Hydrogen is 1 valence. Since there's 4 of them, it's going to be 4. So the total is going to be 9. However, there's a plus, so we minus 1 from that, and the total would be 8 valence electrons. And again, what we talked about with hydrogen is that it can only have 2. So if we have nitrogen in the middle and we have 4 of these hydrogens, we should be okay in theory. So let's check. Okay, So in this case, we have 8 valence, and we only needed 8, and so we're okay. Because we have 2, 4, 6, 8, and since hydrogen only needs 2, we have the brackets, and we also have that hydrogen only needs 2. The next one is cyanide. So this one is a bit weird. So carbon has 4 valence. Nitrogen again has 5 valence electrons. And then the total would be 9, but we have to take into account the minus, so that gets you to 10. So it's 10. So let's try. So in this case, there's not necessarily one central. In these previous examples, we've seen clear winners for the central atom, and which ones were our terminals. But in cyanide, there's not really a terminal or a central. So all you really have to do is, there's nothing to worry about. Just draw them both. So now this is where things can get a little bit tricky. So I would just draw the bracket first so that I don't have to worry about forgetting the bracket. Now this is where it gets weird, because even if you can't, 6 times 2, it just doesn't make sense, because we have 12 plus 2 is 14 with too many electrons, right? And we're overextended. We can only, it has to be this golden number of however many valence electrons. You just have to use those amount of valence electrons available. You can't go over, but you can't go under. So that's where it gets tricky. So if you add a bond, let's say you have a double bond. So if I have a double bond, now I can only do 4 on each side. So that'd be 4 times 2. So that's like 8. 2 times 2 is 4. I'm still left with a problem. I'm still not to 10. So let's do a triple bond. So if I do a triple bond, now I can only do 2 on each side. So because it's already 6 in the middle for each. So that's 2 times 2, which is 4. And then 3 times 2, which is 6. Boom, I got 10. I can go on each side, and that would be my answer. So that's definitely a tricky one in consideration to how it only has 2 elements in it. So number 6, XeF4. So in this one, we have a clear winner for the central atom and the terminals. So fluorine is the terminal, but we have to count. So one of my bad habits is I don't count. Sometimes I get ahead of myself before. So xenon is going to be 8 valence. It's kind of funny how this is true. It can occur. It's already stable. Already has 8 valence. And then we also have fluorine. So that's going to be 7 valence times 4. Since we have 4 fluorines, is that 28? And then that's going to be 36. So no brackets this time. And so let's see if we can be okay with just leaving it as that. So 6 times 4, that's like 24. And then 4 times 2 would be 8. So then we have 32. And you're like, shoot, like how would I How would I get to 36? I used up all of my dots. How can I get more? Because each of these elements can only get to 8, right? Well, that's where the exceptions come in. And specifically for this one, we would get 2 more lone pairs on xenon. And that is because as long as you're in the third period or below, you're going to be able to hold more valence electrons, expanded octet, since the d orbital, you have access to the d orbital, and so that's really how you get to that position. So you just have to be aware that once you've hit that third period and below, you're able to expand your octet. Number 7. PCl5. So we have a clear winner for the central atom. We have a clear winner for the terminal. And you're like, what is going on? You have 5 chlorines. And again, I'm getting ahead of myself. I'm not counting. Phosphorus has 5 valence. And chlorine has 7 valence times 5. So that's like 35. So you have a total valence electron of 40. So if I did my little shortcut, 6 times however many phosphorus I have, so that's 5. I have 30. And if I have 5 bonds, I have 10, that would be 40. And again, as we've stated, the fact that as long as you're in the third period or below, you're able to expand the octet. You aren't just limited to 8 valence. So that's why this one works completely fine. You just have to make sure you draw in such pairs. So yeah, these are some of the weird things about Lewis structures, but it gets repetitive in a sense because you're doing the same thing. So in summary, you basically count how many valence electrons you need in the particular question, and you sort of just map it out. 6 times however many, and if it doesn't work, try adding a single, double, or triple bond, as we did in the cyanide problem. And if you have a charge, you have to kind of account for that. So you have to make a bracket, and you have to put the charge on the top. And if the element is in the third period or below, you can expand the octet, as well as you can also put lone pairs, if necessary, on the central atom. And lastly but not least, you have to make sure that the amount of electrons is the same. It can't be above or below, it just has to be just right. So thank you for watching this video, and I'll see you in the next one.